This podcast is supported by Siemens, your partner for industrial-grade AI.
Hello everybody and welcome to a new episode of our Industrial AI podcast. My name is Robert Weber and it's a pleasure to talk to
Peter Seeberg. Good morning, Robert. Good morning, afternoon, evening, dear listener, wherever you are.
Good morning, Peter. Let's start into the news part. Peter, do you remember, I think it was in autumn last year, our first episode with Sepp Hochreiter and xLSTM?
Is it where he said he was close to explode or?
Yeah, exactly. I don't know if you remember, I had the question back then, and my question was, even if you don't manage to build the best LLM in the world, there will still be many other applications on xLSTM in the industrial sector and time series, for example. And voila, here we are. We have the best RNN in the world, but we also have a lot of, I would say, it's crazy. Every week we hear something new from xLSTM. We have this vision approach, and now we have the time series topic. I think that's very, very surprising, right?
I think Johannes at our AI in the Alps conference, he was probably asked, and he explained how it was kind of, not sure who was it. Was it Max or was it, I think, one of the other guys? And I think Johannes was saying, we need to concentrate on things. And of course, he's in charge of that, of a certain specific side of the research. And he said, we're going to do this or that. And then he was kind of laughing because, smart guys, smart women, smart people, they do whatever they think they need to do, right? Was that one of the researchers overnight just tried xLSTM?
It was the vision approach.
On vision, right, yeah. And, look at that. It works on vision as well. And now, and I'll talk about it later, or now there's these guys who build a system for time series on xLSTM.
Yeah, right. Should we go a little bit more in details, Peter?
Yeah, sure, I can do that. It's called the xLSTM Time. It's by Musle Al-Harti, Usev Mahmoud. They're from the University of Bridgeport, USA. It's about long-term time series forecasting with LSTM. Not going to go into too much detail. Of course, they talk about how Transformer have taken a lead position the last couple of years, not only in language processing, but also specifically then time modeling. They concentrate on long-term time series forecasting. They have an acronym for that, LTSF. We need to be careful. There's so many.
Yeah, so many L's.
Now, basically, what they do, they discuss, what xLSTM is. They talk about the two architecture variations, the sLSTM, mLSTM. Some of you, the listeners, have heard about the guys talking. The one is the stabilized. The second one is the matrix. I'm not going to go into the details. I do believe, it's probably on the border. I am interested, I must say that, and maybe I'm convinced that in the near future we will be hearing a couple of other times. Maybe that's exactly the level where still these guys say that they are, I believe, using the first one for the smaller data sets and the second one, the mLSTM, for the larger data sets. Now, if that is what the designers, Sepp and the team around him, have exactly meant it to be, I'm sure we'll hear about that later. Now, what they're doing is they compare their xLSTM-based solution with a range of transformers, which I had not specifically heard of, but some of you, the listeners who concentrate on time series, may, fatformer, autoformer, informer, piraformer, but also a couple of linear solutions. So there have been also already in the meantime linear solutions, patch, TST, D-linear, and basically they outperform, I would say, I believe 95+% of the existing approaches. Now, as has been the case many, many times, they build, they train data from electricity, traffic, finance, weather. I think weather we talk about later on anyway today, and which typically has a granularity. I think that's the term of minutes to weeks. Every minute or every 2 minutes, or in one case, even once a week, you get a data point, right? Now, what I am very much looking forward to is to have you, Musle or Osif, or any of you, dear listener. I believe, I understand they made the code available. So any of you should be able to use the code and have it train on a typical milli to nanosecond industrial data. And that's what I'm, as always, very much looking forward to. I mean, you can't be certain, I guess, there's something that works on second data that also works on milli. Maybe you may make an assumption, but assumption is not good enough. I'm looking forward to have some of you specialists in the industrial area run this solution against a typical industrial time series data.
So they haven't investigated industrial use cases, right?
Well, not as far as I can see. Well, I mean, electricity, I guess, gets close. But as I said, even the electricity is a typical, a minute, maybe every 5. Did I say minutes? Yeah, I didn't see even seconds on there, right? So, our industrial data, sensors, whatever we're measuring, it is not always the case. You do not always need to measure a pressure somewhere every millisecond. But then our PLCs are a complete deterministic system of when does my signal need to be back within what time frame is typically a millisecond and goes even further down towards a nanosecond. So I think it is important for us that we know that if we want to forecast what is happening in our production line, it is based on time series data that have a granularity of milliseconds towards nanoseconds.
Okay, that's really interesting. So please contact us. Please try out. Maybe they haven't investigated industrial use cases because there are lack of data for them. Maybe it's a problem. Yeah. It's. I think many of these we have seen before. They just use what is available. I do believe we do have, but you may be right. Relatively, the relative lack of. So maybe you guys, you here, or you, dear listener, who have not been involved in this specific project, you can take it and run it on your industrial data. Perfect. I have another news item from Dubravko Dolic from Continental. Greetings to Dubro. He was already been our guest, and his company has rolled out a new AI-based product. And I have a quote from Dubro: "Years of development on AI-powered tire sidewall readings culminates in its first process automation integration." So I think it's a vision-based tool, and Dubro has already reported on this in the podcast. And now Continental is rolling out the application and put the whole text in the show notes. So the link is in the show notes. It's a very interesting approach, or you listen to Dubro in the podcast. Kudos to Dubro and his team. Great example how you build a product out of AI, and great to see.
Is it production based? Or they're using this inside of their tire production?
I think it's for their customers to check the tires and stuff like that. Yeah.
All right. Yeah. So then it's still part of it. Yeah. I'm asking because I think even when you're driving a car, we're still allowed to drive a car these days. Yeah. We're not going to go into the politics of the kind of fuel that you may or may not use. That's, I believe, currently possibly changing, at least in the European Union, or if it's battery or whatever. It's not necessarily our topic, unless we're using AI as part of it. Another reason I'm asking is that I believe even while driving, you could call that almost like inference. There are systems exist that, and maybe they're even necessary or implicatory. On the European Union very soon, our cars are not allowed to be sold if those systems that check for the pressure in your tire.
Yeah, exactly.
But I believe what you're saying is Dubravko uses it or his customers use their solution in their end of line, maybe quality check, right?
No, I think it's for the customers when you have a lot of trucks and you want to check if the tires are correct. So it's a life cycle management, I would say, for tires. And it's an app, and you can take your camera from your smartphone, and then you go next to the tire, and then he will read out all the information from the tire. Yeah.
All right, there you go. So it is in the direction of what I was saying. Well, I would call it inference time, but it's not inference. But it's not a part of the production. It's not part of the training, but it's part of using it in real life, so to say, after the tires have been produced. In this case, even after they have been on the road for many, many kilometers or miles. Okay,
exactly. I think it's all about documentation. If you have a lot of trucks, you have to document. You have your documentation, what kind of tires you have, how old are these tires, and stuff like that. Yeah, and they call it a sidewall reading. So I think the sidewall, this, it's a tire for the winter. How old is it? When was it produced? How the size of the tire and stuff like that. Yeah, and then it will automatically go into the documentation. And I think that's a smart approach. It's a vision approach. And you can hear more in the podcast with Dubro and more in the show notes. I don't know if you recognized it, but I was very touched when I read Jakub Tomczak's post on GenAI systems on LinkedIn, because he summarized his ideas from your podcast and wrote a summary, and he dedicated the paper to both of us, Peter.
That's huge. Yeah.
Yeah, that's huge. I was flashed when I saw that. Yeah,
it's amazing. Yeah, maybe quickly to summarize. Because you can listen to the podcast, only a couple of weeks old. Jakub, he put his thoughts first down in let's say an essay, 1-2 pages. I think it was on LinkedIn, and then a couple of weeks later we discussed it in the podcast. And now he's put it a lot more detailed into an official paper, Generative AI Systems, the systems-based perspective on GenAI. So very quickly, maybe not to go into too much detail, but number one, he confirms how LLMs have revolutionized the AI systems by enabling communication with machines using natural language. Yeah, that's what we started off with 6 years ago, right? Remember the Zepp's famous quote, talking to a machine. Now, recently, very interesting, you just mentioned Dubravko, Conti, vision, these systems have been extended with vision, now. So now those systems become multimodal, audio, video, text, whatever. And then those of you that have heard already the podcast, and those of you that have not, that's already enough reason to go into, because he introduces this term, right? Spelled out as GenAI sys.
Genesis.
And he makes a very funny kind of play on words, because he then, because I called it, GenAI sys, and he says, Genesis. Oh, he's really talking Genesis. Listen in the podcast. So they're now capable of multimodal content creation, sure, generative and decision making, right? You have access to databases, to specialized tools, and basically he explores, new research in GenAI systems. How to build them, how to design them, how to build them, how to train them. And he calls out for a cross-disciplinary approach to answer questions about the inner workings of the. So go to his paper. If you want to hear Jakub talk, then you can go back to the podcast a couple of weeks back.
Yeah, it's a very interesting podcast, and I've never met a guy like Jakub. He's so nice and so open-minded. I'm very impressed by Jakub.
Yeah, we'll see him again when? Latest?
In October at AI at the Danube. Yeah, he will held one working group, and he will talk about GenAI systems for sure.
And then most likely again in December?
No, in January at the Hannover Messe Industrial AI Conference.
But I think there's a Vancouver event before that.
Yeah, Vancouver, sure. I forgot Vancouver because he's a share of NeurIPS, and we will meet him in Vancouver. But I'm not quite sure because the hotel prices are rising.
Oh, really?
And, maybe we have to rent a camper or something like that, Peter.
I'll bring my camper from Munich.
Yeah,
Vancouver.
exactly.
Oh yeah, but it is very important. Why are we so proud? Not just because we love Jakub as a human being, as you just said, but also, he's not just somebody. He's the program, one of the program chairs of the world's most important AI event in Vancouver, this beginning of December this year. Yeah.
Exactly. And in Frankfurt, he will also be a part of the conference. So you can meet Jakub 3 times in the next 6 months if you want. And I have one more news because there's a new company on the market. And yeah, we have a lot of AI companies, but this company is quite special. It's called xAI.
Oh, Robert, you need to do better research. The company is called World Labs, and you've had it nicely put together at X-. So, Fei Li's company is called World Labs, and they received a lot of money. Be better prepared next time.
And the idea of this company is to extrapolate images and text into 3D environments. That's huge. That's interesting for engineering. Greetings to Jan Seiler from Festo. I think you have to take a look at this company. And behind it is Fei Li, and she's often called the godmother of AI because she developed, for example, ImageNet, and everybody knows ImageNet, a key visual database for object recognition research. So very, very interesting approach to extrapolate images and texts into 3D environments. Interesting, very interesting.
Did we discuss that in the Alps as well? And was there a reference to the company, you're so good at names, that we talked to like a year ago, a Munich-based company? They extend...
Werk 24.
Very good. German name Werk. It's almost like the BMW for work, for fabrication. Because they have been doing at least something similar, all the time. You have a 2D drawing, and you have no clue anymore because nobody put it down. What does this mean? What does that mean? And they extend. So they've been doing something similar, but maybe what interesting, another X, NXAI. Now there's X-AI. Interestingly, everybody's doing X's for whatever reason. I don't know.
But I think it's more than Werk 24 because you extrapolate really text into 3D. That's crazy.
Yeah, sure. Yeah. Well, but then again, we're looking forward to have Werk 24, reply, let us know if that's what you see as well, or if you're maybe moving into the same direction. And at the same time, of course, very much looking forward to what Fei Li is doing there.
Perfect, Peter. So I have one more listening tip because the OPC Foundation podcast with a great Peter Seeberg is dedicated to the topic of OPC UA as a knowledge graph. And it's a great episode, Peter, I must say. And I'm really looking forward to the AI working group that wants to get together in autumn. And you did an interview with Holger Ken. I will put the link into the show notes. It was a very interesting episode. I listened it on the weekend, and yeah, it was very interesting.
It was so what is so nice and interesting, and I've kept on telling it, and I will, because it will become even stronger, that everything is kind of coming together. And I always give this example, because of digitalization, automation, digitalization, AI is just the top of it. If there's something beyond that, I guess so. But and everything comes together. And I always say, because we always, we are the Industrial AI podcast 6 years now, but I've mentioned it a couple of times that very soon you're going to see, physical doctors, they're going to use a small whatever, maybe they're going to use their smartphone, and they're going to have everything on it. They're going to listen, they're going to look, they're going to do all the things that we talk about. And that's why I'm not, but the point is that everything is coming together. And Holger was at our AI in the Alps event as the representative of the OPC Foundation. And as we got up and went down the mountain, which mountain is that?
The Arlberg.
That was the Arlberg mountain in Austria. We started talking about, this and that, and that was so nice. And at the end, when we did arrive at the hotel Friday afternoon, 5 p.m., it was, we said, okay, why not discuss this, which is OPC UA for AI, not the other way around, working.
Yeah, for AI. That's important. Yeah.
Which is so good. You know, you and I, we do the podcast for the OPC Foundation as well. So they are only two things, but it's all coming together, right? It's everywhere, looking into algorithms, looking into the data, and finding things, seeing things that we as humans cannot see. And yes, to close this off, the big thing that we see in our area is combining symbolic and sub-symbolic. Sub-symbolic we've been doing now for the last 50 years, machine learning. Still have been, I would say, I don't know, a couple of hundred, probably a couple of thousand, 10,000 people who still have always concentrated on the symbolic side. So which is then typically what today's are the knowledge graphs. And now the big thing is bringing it all together, right? You know, I'm having large language models providing with knowledge graph based information. So their outcome will be a lot better than if you do it without. And for our industrial world, you know, it's very clear for me that OPC UA is the standard, which with its information model is a knowledge graph. And therefore, I'm very, very much looking forward to hear what is going to come out of this new working group.
And for me, it was interesting because Holger and the OPC Foundation will open the group. It's not only for OPC Foundation members, as I understood, because he wants to have it more open and he wants to have more AI companies joining the group. And that was surprising for me, yeah.
I think it's Stefan somewhere mentioned as soon as they opened it, they had within short time 60 companies say, "Oh, I want to be part. Yeah, I can not sure how they're going to organize, but I can very well imagine that it's going to be a huge effort, and I'm very much looking forward to. I've been stating a couple of years back to say OPC UA makes AI fly in the industrial space.
Exactly. Peter, let's switch to the main part because we were at the AI with Purpose Summit by Siemens and recorded some episodes. And this is the first episode with Johannes Brandstetter. And you talked to Johannes about the weather because this is an industrial AI podcast where you talk with him about, why you discuss the weather with him.
And remind me, was it actually, that was before, I believe, he did his presentation. It was one of those where you started 5 years ago. There was a point we were still recording physically, on site, and there was one, and I was always kind of supporting you, and suddenly you said, "Now, Peter, now it's your turn." You recall that? I think it was here in Munich, actually. And this was one of those. I think you just introduced me to Johannes, and you said, "Okay, Peter, just do your thing." So it was kind of an unprepared. I'm not sure, but I had written, of course, about. And then on the same day, Johannes and Albert did their presentation. And it's all about the introduction that Johannes does. And it is very, very nice story where a couple of years back, Johannes moved to Amsterdam from Linz. He has had a great time there. He didn't really want to leave. And he started at Microsoft with a team. I think he initiated this new weather model. And he's saying, "I know nothing about the weather." And there was something at some point in time, I think he was presenting to, 100, real specialists in the weather world. And they soon understood that, that he doesn't know a clue about the weather, but they already were convinced that the AI-based approach was going to change everything. And that model has now become officially available through Microsoft. I believe it's called Aurora. And he is completely convinced that what they already can do today. And with the weird weather that we have here, I believe in Central Northern Europe, it's becoming so weird. You're looking at these apps and they have absolutely no clue anymore.
No clue.
So I'm really, really looking forward. Now, the point, of course, is, and again, it's about, Johannes is a physics guy, right? And he does all in xAI. He's in charge of the simulation, right? And his point is, he started with the weather, and what the algorithms that they have applied to the weather, to the data on the weather, he or we can in the future apply exactly the same way. It's all about simulation. It's all about kind of looking into the future. It's about making a model looking at something. And I've said it before, like what I did, architecture, you paint something which doesn't exist, and you do it for yourself or for your customers. And you like this or you like that. And these days we talk to the model, and the model. So, but it's a 180 degrees change of the way that we will be doing this simulation, this looking into the future of how the world may be.
Yeah, it's very interesting because I was a guest at a large energy company, and they asked me to hold a presentation about AI and what is the future of AI and what do you see. And I presented the ideas by Johannes, and I showed them Aurora and what does it mean for industrial processes and for energy processes. And like the expert for the weather modeling, they were so impressed that they were so, oh my God, this will change everything. What is our USP in the future? Everybody can build simulation of our processes. That was the main topic after my presentation, right?
I can imagine. And for me, it's the same. It's so, I'm not sure. I mean, and it's always like what I really do not like is these discussions where, without mentioning names, it's like, oh, this is not the whatever. This is not AGI, and it's about. It doesn't matter. It doesn't matter, and we've never used that anyway. We don't have people that in our podcast that talk about this AGI, the general AI. But I think what we must kind of confirm that what we see is that the world is changing. Everything is turned upside down. And it doesn't matter what we call it. If we call it machine learning, symbolic, sub-symbolic, everything is changing. And in the weather, you need to imagine, the weather has been looked at for probably 2,000 years, or as long as Earth exists. We have these famous rules here in Germany. I guess everywhere, the people dependent on the weather. And, let's say the farmers are just one example. And I'm certain that the farmers in the United States or in China, they have the same knowledge as the farmers in somewhere in Europe. And over hundreds of years, they have these rules. They know exactly if on day X something is this, then that is going to happen. It's exactly like that. Now, that is our human capability. And if we then have the algorithms look into the hundreds of years of data that we have, they can do, 1,000-fold better, and than what it is that we're capable. And the same thing for physics. What does it mean? What are students going to learn these days? When they're in school, then they get to the university. In how far and these days they learn maybe from 4 years, they learn 1 year about the physics, the basics, all the formulas. Are they still going to learn that?
Yeah, I think so. Yeah.
I believe so, but probably not as much. Probably not as much, because as soon as they get out there and they need to deal with, they're going to use algorithms, and the algorithms are going to look into the data, and they come up with the regularities with the simulation, and then and maybe they can still check and test. I'm not saying I'm not saying that they shouldn't be able to do that. They will be able to do that, but what they are actually going to be using in the field is, the algorithms that look into the data and say, this is how it's going to look.
Exactly. And we must come to an end now, Peter, because we can discuss 10 more minutes, but we have the main part with Johannes. And it's a very great interview you did with Johannes without preparation. And I'm really looking forward to hear. Thanks a lot, Peter. Greetings to Munich.
Greetings to you, Robert. We'll see each other soon again. Greetings to you, dear listener, and hope to have you soon again. Bye-bye.
Bye-bye.
So I'm sitting here with Johannes Brandstetter. It's, what is today? Monday morning. We are at the Siemens AI for Purpose Summit. And we're going to have a talk here today. Maybe we start there. I think you're talking, is it this afternoon actually? What are you going to be talking about today, Johannes?
Yeah, first of all, thanks, Peter. Great to be here. It's nice to be in Munich, nice to be at Siemens AI Summit. So what I will be talking about is, of course, our company, xAI, our endeavors with xLSTM, how we go further, how we envision our next steps, but also a bit about AI for simulation, which is my personal baby, and it's now the time for simulation to kick off. So I will try to wrap this up.
very much looking forward to. We just had a presentation already, and it was about using, I would say, a combination of large language models in the front, of course, and then combining it with some kind of knowledge base in the bottom. But that was more in an engineering environment, but they were using it to see what had been done in the past. And I was going to ask him, and I didn't. But of course, that is your big topic. How is simulation going to change? And I recall that you had this wonderful example last week. I think it was actually a Microsoft-based, like a weather solution. Maybe you can use that example of what you see, how the weather forecast is changing, and then tell our listeners how you see that way of doing things change in the simulation approach as well.
Yeah, I think you're talking about Aurora. Aurora is the new weather model from Microsoft. I was heavily involved in this project until I left Microsoft. It's very close to my heart because the idea is so fundamental to how we do simulation nowadays with AI. We not learn to simulate or not learn to reproduce one single data set. We learn to reproduce the whole data sets, the whole system of weather models we have out there. And this unlocks new capabilities. And Aurora is really able to predict extreme events, predict sandstorms, predict atmospheric patterns, which standard models, both neural networks and standard numerical simulation, cannot do. And this is the way simulation will enter now the whole industry. If you think back 2 years ago, it was unthinkable that weather models will really change, or AI weather models will change how we predict weather forecasts. And now it's actually reality. And the same speed we will have in different areas. And that's actually what we're working on.
Now, let me try to understand. And I was actually looking yesterday. I just came back from 2 weeks of mobile work, as I call it, and I want to be specific, it was exactly southern Italy. And then we come back to, in this case, to Germany, to Munich, where we are. And I looked on a European level, and I saw this, I can not call it differently, this weather system which is moving around with almost like, I believe, the northern of Germany in the middle. Now, I understand that this system that you've been working with, and I want to just go into it as for better understanding than moving towards simulation in an engineering environment. I can understand that if we take all the data that I believe one of the satellites or many satellites have been taking, so we look into the data and we ask the algorithms, to tell us what they have seen, help us. How can we do that in engineering products? We just had Siemens Healthineers here on stage. So when the Siemens Healthineers, as an example, engineers are going to design a new tube, how can they use this new approach of foundational models of generative AI?
I would like to rephrase the question into how we get these foundation models in the first place, because this is the key question. And if we think of weather modeling, what I already said before, the standard approach was to use 1 or 2 data sets, which were always the same data sets, real weather measurements over 20, 30 years, and train on those measurements. The problem is you cannot do much with those models. You can do global weather forecasting, but you cannot hone into regional weather forecast. You cannot predict extreme events. You cannot predict atmospheric behaviors, and so on and so forth. So the key difference in Aurora is to ask how we get more data, how we can incorporate more knowledge to that. And that's actually very easy because there's so much weather simulation lying around. There's petabytes of weather data to be downloaded from many, many different resources. And I would say the very same thing is true for industry, because the simulation principles, be it like discrete element methods, smooth particle hydrodynamics, fluid dynamics, they are always very, very similar. What is different is the parameters, the geometries they interact with, and so on and so forth. So the question to ask in the first place, how can we scale up these things? And if this is done, I think downstreaming, fine-tuning it to the tasks at hand is not so difficult anymore. But the first real challenge is to make this step away from this traditional way of doing simulation and to scale this up. And that's actually what we're doing. And we're talking about tens of millions, probably hundreds of million particle simulation, because this is where the fun starts.
Which is a topic that Robert and I, and in the conferences that we do, and you're going to be with us very soon at one of those conferences, that we've been talking about in this case specifically, an industrial foundation model, a topic today here as well. I mean, of course, data is the foundation, the big foundation of whatever we do in artificial intelligence, in genAI. So still trying to understand what young people, and for the continuation of your life, what you learn is basic physics, right? So you need to base understanding of physics. For example, the weather, or how do machines work, and based on that knowledge, and the knowledge is represented through equations, through all kind of laws. And on top of that, in combination with simulation, that is the normal. Maybe there's another word, the forward-looking designing approach. And now, can I look at the foundational model-based approach as looking more like backwards into the data? And let's try to see what it is that algorithms can learn and tell us what they can find in the data. Is it these two directions that come together, or?
That is a very good analogy. So what neural networks always do, if they are not sure if to go left or right, they go into the middle, the average. So if you give the network more simulation, more different kinds of data types, we need to tell the network where they are different. So let's think of we give the network some fluid simulation of a car in a wind tunnel. We have to tell the network what's the difference, what's the speed difference, what's the difference in pressure, or whatever. And the other underlying physics the network can figure out, because it's the same for the different simulation. And the same is true if we simulate in different geometries, if we simulate different materials, and so on and so forth. We always have to tell the network what's the difference, what's the parameters which change between these simulations. And if we do that correctly, and if we encode that correctly, the network can learn the underlying physics, which then is descriptive for all these processes. And that's the key component. If we do weather simulation, we also have to tell the network, is this coming from a simulation? Is this coming from actual weather data? Is this climate simulation? Is this weather simulation? And so on and so forth. But the underlying equation, the network can then figure out itself. And
Very good. You came in today to Munich. You just said from Austria. You're based in Linz at the moment. But you have been for, I don't know, maybe you want to share with us, for a couple of years in Amsterdam. You were working with Microsoft, and you have decided to move, I believe, back to Linz. Why did you move back to Linz?
Yeah, that was a big decision, and not such an easy one. I mean, you know it yourself. You're from the Netherlands. Netherlands is really an AI hotspot in Europe, and it's a very, very nice place. I have this urge in me to build something, because I see that we are falling behind in Europe. I mean, I see what's going on in the US. I also see what's going on in the UK. There's a few good places in Europe, like Switzerland, nowadays Paris, Amsterdam, Berlin. But I want to have such a hotspot in Austria too. And there is a lot of these topics which are actually very, very, very fundamental for our industry and for our whole system. And that's what we're working on. And that's a big driving motivation. So I would say I learned a lot from the Netherlands. I'm very, very Dutch in my heart and will always be. But I decided to have the Austrian part from now on.
Okay, we're all living in this global village. Now, did you study yourself in Linz actually as well, or not?
I studied in Vienna.
Good, but you've moved back to a team of people around Seb Hochreiter. I believe I can say Seb is a friend of our Industrial AI podcast. So you're now with a team around him. Tell us a little bit more about what happens on the university and what happens at xAI.
Yeah, we have this big chance to build a hub, and a hub needs both things. A strong university where actual people come and where people are motivated to study, to do their PhD, also from abroad. And industry where people have the chance to take on jobs, where people have the chance to work with people whom they can learn from. And that's at the moment at xAI, we need to get like really, really good people. We need to hire people from abroad. We need like specialists, really like senior researchers. And these team we are building at the moment for two different strings, for large language modeling, driven by our xLSTM, and AI for simulation, driven by our simulation products. And for those teams, we are really trying to push NXAI and to build up teams. And on the other hand, we have our university, which we try to connect with NXAI, where we want to give the PhD students the chance to work with these people, to work with on these topics, and to give them also a future to see their opportunities to stay in Austria, to see things growing. And these are the two strings which are not so easy to keep together and to unify, but we're trying our best. And so far, it seems to be very fruitful.
Now, as far as I understand, but you need to maybe clarify, you mentioned the two tracks. I think it started probably with just lately with the xLSTM, maybe, and I maybe want to move into the simulation. I hear you say that maybe in the simulation track there's other kind of approaches, but maybe let's stay for a moment, just as a reminder. We've talked about it before, but as a reminder, let's stay with what was the value of the LSTM approach and what did the team around SEP, I assume including yourself, actually do to bring it to the next level towards the xLSTM?
I will try to answer that, but first, one sentence. I see those two things coupled, because why? What sets us apart from other labs is that we have like really two streams. Both of them are very important. Both of them are built on the principle of scaling. And if we scale in one of these areas, we can scale in the other area as well. And these synergies are actually the valuable thing. And that's what me and Sepp 100% agree. So now let's talk about xLSTM. xLSTM is coming from the very fundamental idea of semantic understanding of the long short-term memory architecture, which was, and still in many applications, is the number one deep learning architecture. Of course, in scaling and language modeling, replaced by the transformer. But LSTM functions very differently. It's a recurrent neural network. It works on semantic understanding. You can think that the transformer reads a book by looking at all words at the same time and then predicting, so to say, the outcome of the book, whereas the LSTM reads a book as a human does, from the first page towards the end of the page. These are very fundamental different approaches. And the thing is, LSTM never had the chance to play in the league of transformers. It was never scaled up properly because it needs a very specific tricks to do that, to make it really work, to make it parallelizable during training, to make the memory bigger, and so on and so forth. And that's what we did. So we scaled up LSTM. We have now the best working recurrent neural network. And now, of course, we have to play with the big guys and we have to scale up xLSTM. So we have to get to the dimensions of parameters, talking about billions of parameters, 7 billion, probably 30 billion, where all these language models are. And then we can really see how far we can get and what we can leverage of this recurrent fashion that LSTM is still having and which makes LSTM so unique.
So that is exactly what you've been working, let's say, behind the curtains maybe, but you went kind of public with the algorithm. Is that the right way to say it? Was it actually last week, I think? So you put it, one of your colleagues, you put it on GitHub, and now you kind of handed it over to the community. Is that a right way to put it? And you say, community, here it is. This is our technology. We've talked about it now Sepp announced it like a year maybe back that he's going to do something. You've been building it. And now you've handed it over and you're now saying, community, here it is. Play with it. Let us know what you can do it. And at the same time, we can talk about that as well. You brought 2 different projects, I believe, to the market. So maybe talk about that a little bit.
Yeah, so first of all, it's very important to let the community be part of this. Only the millions of people out there and trying things, all the hackers, they can make the difference. But of course, internally, we write the fast CUDA kernels. We try to scale these things up. But we are very sure or very certain that xLSTM works in many different disciplines. And one of those disciplines is computer vision. So for that, we basically just plugged in xLSTM as a replacement for transformers in computer vision task, image recognition. And it's doing amazingly well. Of course, there is many things to do still and to scale this up and so on. But we were very excited, and that's why we also put out the vision LSTM, so the first LSTM which can see, and which can see much better than expected. And this is just a confirmation for us that we're on the right track, but also motivation for the people out there that use this code, use this chance, and maybe you can get something out of it as well.
Right. So you've been comparing yourself, I believe, as part of the first paper that you did put into the market, comparing the base technology capabilities in relation to transformer-based solutions, I believe in relation to other kind of newer approaches where you see that you are better than existing like transformers or other solutions. Can you talk a little bit about that? Let's say where you see that you now are, where xLSTM is better than other approaches.
Yeah, so first of all, the one thing which makes this whole mess of deep learning so consistent is scaling laws. So we have these laws which hold for whatever reason, which tell us that if we change the number of parameters, increase the number of parameters and the number of data points, we have this log-log behavior, so that the double logarithmic scale, our model gets better. And therefore, one is really, really keen to see this scaling behaviors for different architectures. And for making xLSTM a real competitor to all these language models out there, we need to show these behaviors. And I think we showed that until 1.3 billion parameters. We showed that we have this similar or even better scaling behaviors to transformer, which doesn't say that we are faster, which doesn't say that we can do all tasks better, but which says that we are at least here very, very competitive with transformers. Now we have to scale this up. We have to show that the scaling laws hold for larger models. And if we do that, we can really capitalize on this difference the LSTM has compared to transformers. We all know that OpenAI and Google with the Gemini team, they are building now huge models. They are going probably over the trillion parameter count, and they have data sets which are unthinkable. But nevertheless, we have a different algorithm, a different functionality, which works quite orthogonal to what transformers do. So if we can show, and that's what we are currently doing, that our method keeps up, our method has the same scaling behaviors, then we can really say, okay, now give us tasks, probably on-device tasks with more semantic understanding, where we intrinsically have an advantage, and then we can capitalize on this advantage.
Okay, very interesting. Can you tell us a little bit about how you do that? I'm sure the team, there is humans, but in the end, there is a CPU. Can you tell us? Can you join with us? Like what it is that you are doing the training on? That's more like the hardware side CPU, but also the models. What is the content that you're training on? For example, are you looking more into industrial as a way to say, that's one thing that we want to be big at, or we believe, or let's say time series, many different things there. Maybe you can share what you're doing there.
Yeah, currently at the moment, we're really looking at language. We're really looking at scaling these things up, as all others do. We're looking what's the best language data to use, trying to get experts on board with data preprocessing, generating our own data sets. And we will scale up in this regard. I mean, for us, we don't want to lie to the world, and more importantly, don't want to lie to ourselves. So we want to show how good we are. We want to see the curves. We want to see what happens if we go to 7 and 30 billion parameters. We're very, very sure that these results will look good, but we need to see these curves in order to really say what we are capable of doing. So that's why we do now these curves. And then for a later point, when we've shown ourselves and the world that we can scale, we can then really look at applications where we shine. And for these applications, of course, we need data beyond language. We need data beyond standard text. And this is what I'm personally also very excited about.
Okay. So tell us a bit more then about the area which you are representing then. Is then the simulation, I believe, as you just said. So do you have, in addition or different approaches than what we've talked so far, the xLSTM, or can that be used in the same environment as well, or is it
I mean, there is some very commonalities, and that is both is recurrent. So a simulation is a time process, so it's a time-dependent differential equation most of the time. So we have something which evolves over time. It's very, very compute-intensive. To make a difference with respect to standard numerics, you need scale. I don't think that with a few GPUs, you can replace numerics. You need to go to real, as always, where it hurts, where it gets compute intensive. These are a lot of things which of course are there to harvest. So we can use our infrastructure from xLSTM. We can use the scaling we have from xLSTM. But besides that, things are a bit different. Language is different than vision and simulations. You can think of, if you simulate something, think of the weather, you have a much more reduced system. So you don't need to describe each pixel of the world as you would do. It was language, you would need a word for each pixel. You can compress the state of the system. And there are many, many other differences. But I would say that there's a lot of common ground, and this is what we are using.
Can you share with us something on the CPU side? Is that an internal thing? Where and how do you train your model?
I'm not sure if I'm allowed to say that. I think we will open source that very soon, and how we have not really decided what's the next step to take here. I think for European standards we are using quite a lot of compute, and we will at least double the compute because things get more intensive, and this is also something which is very cool. But we will see how far we get.
Very good. Johannes, thank you very much. I'm very much looking forward to your presentation this afternoon. And of course, we're all very close with you, and I wish you all the best. Thank you very much.
Thanks, Peter, and thanks for all the support we get from you guys.